Bow your heads, please.
Dear Heavenly Father, we thank you for giving us today. We thank you for giving us tomorrow. We thank you for all you've done for us. We thank you that we have such a privilege. We thank you we are so privileged to have a teacher like Miss Frady. So we ask that you will give us the wisdom and knowledge to learn what she has to teach us. We ask you these things in your name. Amen.
Amen. Thank you, sir. Okay, so first, let's go through your test. Thank you. And some of you be pondering who's going to pray next week, because obviously this is difficult for some of you. Guys, all you have to say is, Lord, thanks for letting us be here. Help. Amen. Do you guys know the shortest prayer in the Bible is, help me, when Peter was sinking? I always like that. You ever done one of those prayers? I have. A help me prayer in an emergency. I had a horse that I was on that was a young horse, and a 125-pound Great Dane came up out of the brush, and the horse freaked out, and I had a saddle on him, and I know how to ride a runaway horse, and I had a saddle on him so I couldn't just dive. And I grabbed the rein, and I pulled his head back to my foot, which usually I make a horse stop, because they'll run in a circle and then they'll stop. This horse was so scared of that dog, he just went straight, even though I had his head back to my leg. And he ran through a bunch of what I call scrub oak, which are the oaks with the thorns on them about that long. And I saw it coming, and I said, that little short prayer, help me. And that tree hit, and the saddle broke and went under him, and he danced on me before, I'm serious, he danced on me before he got loose of me in the saddle and ran. And when I came up, my kids were on other horses, and I'm thinking about my kids right away, but they both had enough sense to get off the horse they were on. They'd been trained that if there's an emergency, you slide off the horse, because then you have more control. So they slid off the horses, and I come up like this, and there's blood everywhere. I ended up with 76 stitches in my face. I thought, and then I checked my teeth, because I thought, oh my gosh, do I still have all my teeth? Because it severed the lip, both sides right here. And it was by the grace of God I had my teeth. I mean, because it slammed the tree. And then as the horse was dancing on my back, literally, because he couldn't get up, he was entangled with me in the saddle, I was still doing the help me prayer. And so when the horse ran off and I got up, and I'm like, and my kids saw me and started crying because I was just torn to pieces, and my husband wouldn't let me see a mirror. When the horse ran back and they came to get me, he's like, we're going straight to the hospital. I go, we can't. I'm full of sand. I mean, I had been stomped into the sand. I go, I'm full of sand. My pants are ripped. I can't go to the hospital like this. He goes, trust me, you're going to the hospital right now. And when I finally had to go to the bathroom and went in the bathroom, I knew why they wouldn't let me see myself, because it was scary. I mean, my face was just all in pieces. So they took me to Shands, because that was the teaching hospital that was close. And this is a God thing. So it's a teaching hospital, so it should have been just anybody sewing my face up. But their best plastic surgeon was on, because he was covering. Somebody had called out, and he redid this lip. I don't know if you can see, there's two parts here. He redid this lip 3 times. He was going to get it right. And I thought that was so funny, because I speak for a living, and so God was making sure, and he's telling me it might die, it might not survive because all the nerves are cut. He goes, but I'm going to do it right. And he literally would do it and pull it out and redo it. And I'm like, oh, just finish, And then they put me on a backboard and wouldn't let me off the backboard for over 8 hours, because they could see the hoof prints all over my back. And they go, there's got to be damage to your back. I mean, literally for over a month, you could see every hoof print on my back. And they go, you've got to have broken bones or something. No damage. They did MRIs, they did all this stuff. No damage. And they kept coming back. They wouldn't let me off the backboard. And they kept coming up going, there's got to be damage. And I said, no, I prayed. They come back and look another way. There's got to be damage. No, I prayed. And I said, man, I know, but I prayed. And I'm okay. That's that little help me prayer. So guys, when there's an emergency, a help me prayer counts. Okay, just help me. And sometimes all you can get out. But I'm telling you, God was so faithful in that. And they eventually let me off the backboard and let me go. And there was no damage to my back. I mean, I was sore and I was bruised. And literally, I could show people my back for a month. You could see every hoof print in my back. And then the thing healed up, which the guy said he thought it was going to die and I'd be left with this big hole and all that stuff. And it didn't. And it was all the Lord. So the next time I spoke to teenagers, the one kid goes, oh, so you had a horse wreck. I thought that was so funny. I go, yeah, I guess I had a horse wreck. It's amazing. I still have horses and I still ride them. My husband thinks I'm insane. Let's not go there. Okay, so Blake, you didn't want to pray for us. Well, you know what? We'll start on this side because Cole prayed for us. So, Jay, why don't you tell us? Let's do our test. What is an atom? Please, sir.
An atom is the smallest chemical unit of matter.
Very good. Smallest chemical unit of matter. Do you not have your test?
I'll do it at home.
Okay, but you did take it.
Yes.
Okay, and guys, I had a lot of people forget it this week. Try to bring them. I know it's the first time. Try to bring them because we will go over them. So even if you've already graded them, tell Mom I'd like you to bring them into class because we're going to all go over them, okay? Thank you. And Jay, thank you. Brittany, would you tell us what a molecule is, please?
A molecule is when two or more atoms link together.
Very good. Two or more atoms linked together. Concentration, please, Jacob.
A substance with a ascertained volume.
A certain volume. I know you can't read your own handwriting. It's a scary thing, I know. It's because you wrote really small, isn't it? Yeah. So it's a volume, it's a quantity within a certain volume. Very good. You could have said quantity divided by volume, and that's acceptable. Okay? Good. Any others that I need to hear? We good? Okay. Thomas, would you read number 2 for me, please?
The whole thing,
Sure, read the whole thing.
Sulfur is a yellow powder that is composed of sulfur atoms. Sulfur dioxide is a colorless, poisonous gas that contains sulfur atoms. Is sulfur dioxide composed of atoms or molecules?
Very good. Molecules. If you can decompose it, it's molecules. Thank you. Number 3, please, Jamie.
While looking at historical grave markers, you will find a statue that is bluish-green in color. In order to read the inscription, you scrub the surface of the statue, and the blue-green color comes off as a fine powder. What color is the statue underneath? It's a copper color.
Good. You could have put copper color, brown, red, reddish brown. Anything that's that basic color would be fine. Thank you. Blake.
Which picture represents a bunch of atoms? Which represents a bunch of molecules? A represents molecules, B represents atoms.
Very good. Thank you, sir. And then if any of these you need to ask a question, just raise your hand, okay? All right. Faith, number 5, please.
You are reading a scientist's notes, and you notice a measurement that is listed as 12.3 kilograms. Does this measurement represent length, mass, or volume? Mass.
Very good. Grams and kilograms or any variation on grams would be mass. Thank you very much. Laura Lynn, would you do 6 for us, please?
What metric prefix means 1,000 kilo?
Kilo, thank you. And Isabella, number 7, please. You don't have to answer if you don't want to, but read it for us, please.
How many centimeters are in 1.6 meters?
Very good. Do you want to answer?
160 centimeters.
Very good. 160 centimeters. Thank you very much. Elizabeth?
An object's volume is 0.12 kiloliters. What is its volume in liters? And I don't know if I got this one wrong.
What'd you put?
0.0002 liters.
Okay, I think I know what you did. May I see your paper? The answer is 120 liters. Cassidy, would you read number 9 for us? And thank you, Elizabeth.
A rock has a mass of 45.1 kilograms. What is its mass in slugs? And that would be 3.09 slugs.
Good. 3.09 slugs. Is that one okay?
Well, could I just put 3 slugs?
That's fine. That's fine, but you didn't flip those numbers.
I just put 3.
3 is fine. 3 is just fine. Excellent. But you didn't get the opposite, like you didn't flip the numbers. That's what I was worried about. So you're good. Okay. And then number 10, please, Maggie.
Ammonia is the active ingredient in many household cleaners. Suppose I were to make up 2 buckets of cleaner. In the first, I take 5 cups of ammonia and add them to 45 cups of water. In the second, I will take 5 cups of ammonia and add them to 30 cups of water. Which bucket contains the most powerful cleaner? This is the second.
The second one, very good, because it's more concentrated. Hang on. So each question is worth 6 points. So if you missed a whole question, everybody start at 100. Never add up in my tests. You'll end up doing better if you do it this way. Start at 100 and take whatever you missed and subtract it from 100. So if you missed 1 problem, take off 6. If you missed a half, take off 3. Okay? Does everybody understand how that works? Yes.
What if you did the extra credit?
The extra credit lab.
Yeah.
Then you add 6 to your test.
Okay.
But that means you did all 4 parts and you made a conclusion. And if you wrote up an extra lab, then it counts as 1 question. So you can add 6 points. So you could feasibly have 106 points on this test. Okay, but later you'll use it on another test because when you average them all together, then it'll help you someplace else maybe where you need it more. So it's always helpful to do the extra credit. Yes, David?
On number 7, I added an extra 0. Is that okay? And then I fixed it.
Yeah, that's fine.
Yeah.
Yes?
I did the 2.03, the extra credit one, and I did not get to do the science, the experiment yet. Could I do that?
Sure,
And
and
show
then-
it to you next week?
Yeah, that's fine. Yeah, that's always a way you can do something if you just need a little bump, but you don't want to do the whole test over again. You can always do an extra credit lab. Plus, remember, you're going to average them all together at the end, so extra credit labs now can help you later when things might be a little harder. Okay? So just a heads up on that.
So I took the extra credit lab for last week. Does this count on this test or no?
Yes.
Okay.
Yeah, because this is all still Module 1. So yes, that does. Okay? But you had to do all 4 parts to get the 6 points. In other words, you did the purpose and the procedure and the observations and the conclusion. Did you do all that?
I didn't do the test, I didn't test it yet. But we did that in class.
Yeah, if we did in class, then just write up what you saw. We okay?
Yeah.
All right, let's put that away and open up to Module 2, please. Everybody look on page 25 in your book, please. Module 2 is about air. And in this module, we're going to study about air. And then in the next module, we're going to study about the atmosphere. And we're going to study the hydrosphere and the lithosphere. And then we're going to study water. Or maybe not in that exact order. I guess I could look at the contents page. But the point is, yeah, we're going to study air, then the atmosphere, then water, then the hydrosphere, then the lithosphere. And then we're going to spend 2 weeks on weather. And by that time, you're really, I shouldn't say 2 weeks, 2 modules, which is 4 weeks. So by that time, you're really ready to study weather because you really have looked at how, it chemically works. And you've looked at the atmosphere and the gases. And so it'll make a lot of sense. So we're building up to that. And it's interesting. Weather's interesting. We all live with weather, one way or another, all the time, right? So, okay. So in this chapter, we're looking at air. And the first thing he tells us is humidity, which is the moisture in the air. We're Floridians. We know about humidity. We can almost cut it with a knife outside most of the time, right? I mean, it's the moisture in the air. It's why when we sweat around here with high humidity, we kind of walk around soaking wet and go, oh, this is nice, And so whereas if somebody was in like Arizona or North Carolina and they sweat, it actually disappears. It's an amazing thing because they have, because they have low humidity. And so let's talk about the humidity for just a minute. And he mentions here how evaporation off of our skin is actually supposed to cool us off. Now that is if the air is dry enough to actually suck up the water that's on our skin, then it does make us feel cooler. So let me explain real quickly. First off, evaporation is just a liquid going to a gas, isn't it? So evaporation is a liquid turning into a gas. So condensation is the opposite of that, right? Condensation would be a gas turning into a liquid. Doesn't have to be water, does it? Okay. And there's this theory called the kinetic theory of matter. And I'm going to use all matter theoretically could exist as a solid, liquid, or a gas. Those are the 3 ways that it can exist. And we're going to use water because we're all familiar with water in its solid, liquid, and gas forms. Ice, water, and steam. Not a problem. Okay, the molecules in a solid vibrate. They're not sitting still. They're vibrating. Okay? And then if you give it energy, which let's think of energy as heat, if you give it energy, then the molecules can break free and start dancing around. Woo, woo, okay, and that's liquids. Liquids are dancing molecules. Literally, that's why you can pour a liquid, because the liquid has enough energy in the molecules that it's dancing around. Actually, water's line dancing, but we'll talk more about that later. And so it's dancing around. And then if you continue to give energy, heat, to the water, what does it do? Turns into a gas, doesn't it? So now it's not even dancing anymore. Now it's bouncing off the walls. Oh, like a little hyperactive kid on caffeine, right? Woo, and sugar. Okay, So that's a gas bouncing off the walls. And then if you take away some of the energy, so we cool it down, we take away some of the energy, it stops bouncing off the walls and it starts dancing again, turns back into a liquid. And if you take away more of the energy, then it goes again and it turns into ice. Is everybody with me so far? So it's got to do with the energy and its movement in the molecules as to what state it is in. Now let's apply that. So if we have a liquid, water, and we turn it into a gas, the molecules that were dancing had to take some of the energy to be bouncing off the walls, right? So when the water is laying on us in the form of sweat, and if it's dry enough outside that it could evaporate, then the idea is that God set this system up so it would cool us. Because as that water turns into a gas, it has to absorb the energy away from our skin so that it can launch into that mode. Does that make sense to everybody? Okay? So that's how evaporation is supposed to cool things. Now we have an experiment that we're supposed to do here. Everybody has a thermometer, at least between every two of you. If not, Cole, you have your own. Okay. Now, part of the trick is actually reading the thermometer correctly, I've learned over the years. And we're going to all write this down together, and this is going to be in your observation section of this lab. So if you don't have it already written up, you're supposed to. But if you don't, get a piece of paper. You're going to put observations for 2.1. And then when you put it together with your other thing, in the observation part, you would just go refer to next sheet, okay, and attach it. So what we're going to do is we're going to do this one together. So first, we're going to read the centigrade. Don't breathe on the bulb. You'll warm it up, okay? Don't touch the bulb. Don't breathe on the bulb. It'll warm it up. You're going to read it in the centigrade. That is with the C, not the Fahrenheit side. Now, everybody look at, because scientifically we're supposed to use the metric system. Everybody look at your thermometer, and you've got to figure out what the divisions are on your thermometer. Like these big ones here, actually between 0 and 10, there are 10 marks, aren't there? 9, and then 10 is the 10th mark. So that means it's marked off to the ones place. I think these small ones are also. They're marked off to the ones place, if you'll look at them. Mm-hmm. Yes, and the big line in between would be 5. Okay, so with that in mind, everybody, you can pick up your thermometer, just don't touch the bulb. Everybody read what the temperature is in the classroom. I don't know if you're going to be able to see that, but I'm just showing you so you can, there you go. So you can get a feel for how that works. And there's the centigrade side, so it's on the left. Okay?
So,
all right, so
21 Celsius, correct?
Whatever yours says. Now what we're going to do is, you guys tell me what's yours. Okay, so 26. What is yours?
24.
They will be different, guys. The different instruments will be different.
21.
21.
24.
24. Ladies?
22.
22.
23.
23.
22.
22.
28.
Boy, that is a big difference, huh? So you're right, and you guys are all counting from the line. See how different, and you're right next to each other. So that's, Abigail, how about you ladies and Aaron?
25.
25. Gentlemen?
24.
24. 23. Boy, this is really going down there. Yes?
24.
24. Okay. For the benefit of those of you in the back of the room, I'm going to rewrite this. Because you're all supposed to have all of these numbers, so please write them down. We are doing this experiment as a class. 5, 24.
All of them or just one?
All of them. Write them all down. See, you're going to see also what you're learning here is about experimental error. You guys are sitting right next to each other, and that your temperatures are different, aren't they? Now, the next thing you're going to do.
If the numbers are the same, do we have to rewrite them again?
Yes,
There's 2
because we're going to write down the changes, and they'll be different. The next thing you're going to do is everybody has a cup with a cotton ball on the table. Now, you don't want to hold the cotton ball too long because you'll warm the cotton ball up. You don't want to do that. But you also don't want it soaking wet. So this is a very fast maneuver. What you're going to do is grab your cotton ball, just squish it once, and then lay it on the bulb. Don't squish it down on the bulb. Just lay it on the bulb of the thermometer. Here you go. So you're going to pick up, squish, and lay it on the bulb. That's enough. And then just lay it down. And don't squish it down. Just lay it there. Okay, good. Just going to lay it on the bulb. Try not to get your books wet and all. Share the cotton ball, guys. Yeah, because there's other people at your table. Okay, it's over your thing, right? Now we're supposed to leave this alone for 15 minutes. So we're going to leave it alone. And we're going to go on with our work. And we will come back to this in 15 minutes. Okay? So what we'll do is go to page 26, please. And he describes for us what a heat index is. Now, the hotter the air, the more energy that it can, the more energy it has, and therefore the more water the air can absorb. So the hotter the air, literally the more humidity it has the possibility for. And somebody tell me, why is it so humid here in Florida? I mean, there's a lot of other places that are hot, like Arizona, but it's not humid. Who can tell me, why do we have so much water in the air?
Because we're covered in water.
Okay, we're surrounded by water, aren't we? Very good. We've got water on three sides and lots of water down the middle, don't we? Okay, so we have enough water that with this heat, it's able to get into the air, and that's why the air is so humid. Now, he mentions here on page 26 about a heat index, and that's a really good thing to have because let's say it's 80 degrees. Let's say it's 80 degrees. Here it's 80 degrees and it's 85% humidity. You go outside and you go, right? In Arizona, you go outside, it's 80 degrees, and you're like, oh, this is nice. I could do this all day long. And the difference is, and people out there get heat stroke really easily. And the difference is what we call the heat index. It's applying the humidity to the temperature. It tells you, a heat index tells you how hot it feels, not how hot it is. So here, if it's 80 degrees with an 85% humidity, it might feel like 90 degrees. So that's why it's 80 degrees, but the heat index is 90 degrees. And that's because the humidity makes it feel so much muggier. Does that make sense? So the heat index isn't the actual temperature, it's the how it feels temperature. And it's taking that humidity into account. Let's look on page 27. And we've got absolute humidity and relative humidity. And so, who read last on the test? Who read last on the test? Did you? Okay. So, Sophia, would you read us absolute humidity, please?
The mass of, wait, this one?
Yes, ma'am. You are absolutely right.
The mass of water, vapor,
Mm-hmm.
mass of water vapor contains in them a certain volume of air.
Very good. Thank you. It's the mass of water vapor in a certain volume of air. Does that sound like concentration? Yeah, it's a mass in a volume, isn't it? So if you want, you can define absolute humidity as the concentration of water in the air. Of water in the air. So it's actually how much water is in the air. Now that's different than the relative humidity. And Parker, would you mind reading relative humidity for us, please?
The ratio of the mass of water vapor in the air at a given temperature to the maximum mass of water vapor the air could hold at the temperature expressed as a percentage.
Ah! Aren't you glad you don't have to memorize these that way? Okay. What I would say to you to know, and relative humidity is actually the one we want, because if they told you the absolute humidity, you might know how much water is in the air, but you don't know how much water it can still hold. Like if I said 80% humidity to you, I'm telling you that the air is full up to 80%. It still only has 20% to fill. Whereas if I said 50% humidity, you know that the air, like a sponge, could still suck up a lot more because it's still only half full. Does that make sense? Yes, sir.
When the air has more humidity, does that mean it would rain more?
When it's 100% humidity, basically it's falling out as rain. Yes. So does that make sense? Because now the air is so full it can't take any more and it's actually letting it back out. Okay? Good. So think of the humidity, now that's relative humidity, and that's what we would use more is that percentage, and that's what Parker just read. How I would define relative humidity is it's the water, let's put water, that's the short way of writing water, water vapor in the air divided by the max water vapor that the air can hold. And that is dependent on the heat, because depending on the temperature is how much. Have you ever noticed that when we have cold weather, it feels so good outside? It's not necessarily just the cold weather, it's because the humidity is low. So that's why even if it gets up to 75 or 80 degrees in the wintertime, you still feel like, yeah, I can do this, you know, and it's because the humidity is so low. So this is a percentage. Everybody can see that, right? Because this is the total that it can hold. This would be like the absolute humidity down here. Wow, we could have just written that. We could have written water vapor in the air divided by the absolute humidity. Would that be right? No, that wouldn't be right, because that's how much is there. It's not how much it holds. It's got to be this way. Okay. So water vapor in the air divided by how much it can hold. And that gives you a percentage, because it's actually a fraction. But once again, if this said 50%, that would mean there's still 50% of room for water to go into that air. So there would still be a lot of sponge availability to pull out. Does that make sense? Whereas here in Florida, I think most of the time our humidity is upwards of 80%. So things don't evaporate very quickly down here, and it rains a lot. And I mean, there's enough evaporation going on to cause all that rain though, right? So anyway, that's that heat. That's why the mornings sometimes feel better than the afternoons, because the humidity is less in the morning because it's just getting started. Okay, let's look at, on page 27 at 2.1. And let's see. We're up to 2.1 is a long one, so I'm going to read that, and then I'll ask Nicole to read 2.2. Would that be okay? Okay. Suppose you left a glass of water outside on 2 different days. On the first day, it's warm and humid. Oh, sounds like Florida. On the second day, it is the same temperature, but the humidity is low. Sounds like winter in Florida. Each day, you measure how long it takes the water to completely evaporate from the glass. On which day will the time it takes for the water to evaporate be the least? It says the smallest, but that's what they mean. Which will be shorter? So you guys tell me, on which day will it be shorter for it to evaporate?
Second day.
Good. The second day, because it's got low humidity. Very good. You guys got this. You know how this works. Good. Nicole, would you mind reading 2.2 for us, please?
Suppose you did the same experiment that was described in problem 2.1 when the relative humidity was 100%. How quickly would the water evaporate from the glass?
What do you think?
Wouldn't evaporate.
Absolutely. It wouldn't evaporate. It's like taking a sponge that you've already sopped up everything it can handle, and then you put it in a puddle. Is it going to evaporate anything? No. Absolutely right. Good. Does that help? That picture help? Okay. Hey, humidity can be we know about humidity, but understanding relative humidity and absolute humidity can get very confusing. And that's why I tried to give you more specifics as far as the absolute humidity is the actual concentration of the water in the air, whereas relative humidity is telling you how much water is there and how much it can still absorb. Yes?
Is humidity related to temperature change daily?
Yes. Yes, it is. It's also related to whether we're in a high or low pressure system. And that actually has to do with it also. When we get to weather, we'll study it more. Okay? And you'll be writing that stuff down and all. Turn to page 28, please. On page 28, we're looking at the composition of the air, but we're going to look at dry air because, once again, we don't want to take into account that changing amount of water that's in there. And we're trying to do a pie chart, and the pie means that it's 100% is in the circle, and then we're doing the pieces of the pie representing the different types of air. I'm going to tell you right now, you have to memorize that the air, the atmosphere, is 78% nitrogen, 21% oxygen, 1% other. And you're going to say that with me because this is something I'm going to have you say a few times because you have to memorize it and you need to know it past this module. Okay, so it's 78% nitrogen, 21% oxygen, and 1% other. Everybody say it with me. 78% nitrogen, 21% oxygen, and 1% other. Let's try it one more time. Wait, I'm missing some people in the back. You guys, work with me here. Look up. Yeah, you. Come on. You ready? Let's say this together. Ready? 78% nitrogen, 21% oxygen, 1% other. Very good. You have to memorize that. Now, those percentages are really very, very important that they're set up that way. I don't know about you, but when I was younger, I was always taught that we breathe in oxygen, we breathe out CO2, carbon dioxide, and that plants breathe in carbon dioxide and they breathe out oxygen. Haven't you heard that before? Okay, so that was what I was always taught. So when I saw that the atmosphere was mostly nitrogen, it was very confusing to me. I looked at that and went, nitrogen? Really? And there's a really good reason for that. Now, first off, we need oxygen, and the reason we need oxygen, and you're going to learn so much about this in biology, you're going to wish you hadn't, but anyway. We need oxygen because our cells burn glucose, which is healthy sugar, kind of sugar you get out of vegetables and stuff. Our body's cells burn glucose so that they can make little batteries that are rechargeable batteries called ATPs. They're adenosine triphosphate. They're little chemical batteries that God made that living systems use. And we breathe air, oxygen, because the oxygen allows us to burn the glucose to make the little batteries to recharge them. You with me so far? Okay. And so oxygen is pivotal to this whole thing. Now, we have a really cool experiment that I don't let the students do anymore because I watch some try to burn themselves up and kill themselves. So I would suggest you don't even, that's why I don't even tell you guys to do this one at home. So in this experiment, you're supposed to take hydrogen peroxide, 2 cups, which this bottle is 2 cups. And it's a new one, so we'll pray it works. There's no guarantee because hydrogen peroxide does go bad. Yeah, the oxygen comes out of it and it just turns into water. So if it, yeah, who'd want to though? It doesn't taste very good. Okay, this doesn't look very fuzzy, does it? Oh, there's a little fuzz in there. I can see a little fuzz. Okay, so let's hope. We're hoping for fuzz. We're putting in here, and I'm probably going to make a mess. We're putting in here some yeast. Hydrogen peroxide is water with an extra oxygen attached. It's H2O2. Plenty of hot air here, no problem. Okay. We go like this. If you blow it up first, it just makes it easier for it to fill if it's going to. And we're trying to, we're catalyzing the reaction. Oh, watch it go into the balloon. That would be so not nice. Yeah. Whee! Hey, we're building a volcano.
We're learning about volcanic eruptions.
Okay, if it'll slow down. Hey, I guess it was livelier than I thought, huh? Whee! Okay, we want to get more. We want to get more.
Look, watch, blow up. It's going to look so weird.
Yeah, it's a weird shape. Don't lose that. I need that, okay? Hang on to that for me. It looks like Snoopy. Okay, I am going to just, you're helping me, so hang on to it, okay? Okay, first, I'm glad it's so entertaining. This whole thing's been rather entertaining. Okay, can everybody see that? If not, get where you can see that, okay? Does everybody see that the candle's lit? If you can't, stand up. Everybody needs to be able to see that the candle's lit. Okay, so the candle's lit. And when I cover it, Jay, he goes, die.
It's struggling to survive.
It will once the oxygen is out of the jar. Okay, it was still getting air in from the bottom. That's why I had to screw it shut. Okay, so what happened there? Why did it go out? Okay, from the lack of oxygen, it went out. Now, We're going to try it, and this way we have 2 shots at it, so let's see. See if we can do this without blowing anybody up. Can everybody see it? Get where you can see it, because this is going to go fast. What you're supposed to see if this works is that the fire should get brighter. Oh, it did get brighter. Does everybody see how much brighter it is? Yeah. Okay, we're going to try this one more time. Going to try. Okay, can everybody see how much brighter it is? See how bright? Okay, thank you for that. So that was successful. Ooh, look how bright it still is. What a mess I have. Okay, we'll just clean it up after. We're going to shut this guy down. Boy, look how bright it is. That's amazing, isn't it?
It's better than a lamp.
It's because it's got so much oxygen in there. I just want to make sure. Do you guys see how bright that still is? Let's see. We got a lot of oxygen in there, huh? We had 2 shots at it, though. Thank you for your help. Do you need a paper towel? Okay. Oh, well, I'm just going to let that go out on its own. Yes, sir.
I heard that if you put a potato in hydrogen peroxide, it
Well, I don't know about the potato, but I know yeast catalyzes the reaction between hydrogen peroxide to get rid of the extra oxygen to make it water and release the oxygen. That's why we used it. And catalyze basically means to speed up without being used up. Okay? I don't know about the potato, though. I'm sorry. I just don't know. There it goes. Okay, I just wanted you guys to see that. What happened there? Finally ran out of oxygen. The reason that experiment was very important for us to see right then is this. You need to understand that the reason fires burn is they require oxygen to burn. It's called combustion, and without oxygen, fires go out. If we add more oxygen, did you see it? Whew, it lit up brighter, it burns faster. That's why oxygen is very dangerous around a lit, like a spark or anything, because whoo-hoo, you get fires, okay? Now, the trick is this. There's 78% nitrogen, 21% oxygen, 1% other. At 21% oxygen, our bodies burn just the right amount of glucose so that we can make just the right amount of batteries and be, well, it's good where it is. If there was more oxygen in the Earth's atmosphere, our bodies would burn up. Literally, when they give you too concentrated of oxygen for too long, you read about it, you get lung damage, you can go blind. It actually causes high blood pressure and other problems. So too much oxygen is not good. So what did God do to dilute the concentration of the oxygen? He diluted it with nitrogen, and nitrogen is an inert gas. That means it's a couch potato. What does a couch potato do? Absolutely nothing. So when we breathe in oxygen, it goes in, lays on the couch, it comes out, lays on the couch, in, out. Doesn't do anything. And that's a good thing because it doesn't interact with anything, so it doesn't make us sick. So it is the perfect gas to dilute the oxygen with. Your book told you that if you increased the oxygen by 1%, it would increase the forest fires by 70%. Which means if there were 31%, and this is what it said in there, if there were 31% oxygen instead of 21%, we would have 7 times the amount of forest fires that we do now. Basically, there wouldn't be able to be life as we know it on this planet if every time we had a lightning strike it made huge bonfires, wildfires everywhere. So it's very important. Plus, living systems wouldn't do well with that high of an oxygen rate. Now, I had a student on the other coast who was required to do oxygen when she was born, like premature babies frequently are, and she goes, was that 100% oxygen? No, they don't give people 100% oxygen anymore because they know it burns them up. And in scuba tanks, you don't have 100% oxygen, okay? In the hospital applications, you do have a higher percent of oxygen because they're trying to help the cells, but you don't want to do that for extended periods because after extended periods, like it caused Stevie Wonder to be blind, who apparently was a premature baby. And in the book, do you guys know who Stevie Wonder is? Okay, he's a great musician from my era. And he's a very talented musician, and it's funny because every time I think of Stevie Wonder, I can see him at the piano doing this. He's blind, and he's playing a grand piano, and he's always doing this as he plays. And he's a tremendous, even if you don't know who he is, you know his music because his music was so good that they made Muzak out of it. Do you know what I mean? He just was a tremendously gifted musician that was blind because they put him in 100% oxygen as a premature baby. There was an Apollo mission that they put 100% oxygen in the capsule. It blew up on the pad. Everybody died. they stopped using 100% oxygen. They just didn't know any better. Okay, it's very dangerous. 100% oxygen, very dangerous. Yes, David?
Do you think that's, in Revelations it says that God will like burn the world instead of flood it? Do you think that he'll add more oxygen?
Don't know. I've always thought of that as being more cosmic because of the level of destruction in Revelation. You guys watched the creation video before classes started, and we're going to study the catastrophic plate tectonics model together. But you remember how much was going on during the flood? Revelation says that there'll be an earthquake like the world has never seen, that the mountains will fold in. That says to me there's probably going to be something cosmic going on. So I don't know about the oxygen rate, but I think there'll be something very cosmic going on. And I have no intent on being here. So I am going to be under the grace of God, not under the wrath of God, because of what Jesus did for me. Just, whoa, I do not want to see that scene at all. Because, guys, that stuff that's being described there, I don't know if you realize this. Before I studied Revelation, I always thought that the devil caused the Great Tribulation. And then I studied Revelation, and it's like, oh my goodness, this is wrath of God on everybody. And it's so much worse than what the devil could ever come up with. It's not even funny. And it's God's wrath. And I'm like, oh, thank you, Jesus, that I don't have to be under the wrath of God. So I'm not saying we won't suffer, don't get me wrong, but not God's wrath. We won't suffer God's wrath, right? So, yes, thank you, Lord. Yes?
When did they stop using 100% oxygen?
You know, I'm not sure. I'm really not sure, but I think it preceded you.
Okay.
Yeah, because the Apollo mission preceded you. And there was a lot of stuff that, you know, they learned from those mistakes. So, okay, let's see. Let's do our evaporation experiment. We're going to reread our thermometers now, okay? So, gentlemen, what does yours say?
22.
22?
Yeah.
22. Gentlemen, what does yours say?
20. Wait, what is it? Yeah.
20. Jay, what does yours say?
It's
16.
Which one? This one over here?
I don't know.
Yeah.
Cole, what does that say?
About 19 and a half.
Okay, well, we'll go with 19. How's that? Parker?
18.
Thank you, ma'am. And
19.
thank you, Maggie. And Elizabeth and Isabel? 20? Ladies?
24.
24. Ladies? 20. Gentlemen?
20.
20. That's a 0. It's a really ugly 0. Gentlemen?
19.
19 and
20.
Thank you, 20. Okay, now, once again, you're seeing experimental error here. You notice there's different variations. Could be how you put your cotton ball down, could be just the equipment. But what do we see in every situation, 100% of the time? We see a decrease in temperature, don't we? And we see the decrease in temperature, so how would you write this up? You would put, you know, lab 2.1, and then the name of the lab was evaporation and temperature. For the purpose you'd put to learn more about evaporation and temperature, okay? The procedure, you know, you can write that up, best you can. This is your observation section right here. So your conclusion would be evaporation, something like this. You're stating a fact. So evaporation is a liquid turning into a solid, to gas, I got it. A liquid turning into a gas, and for that to happen, energy has to be absorbed by the molecules, right? I just told you about that. And we see that that energy is absorbed by the molecules and it's removed because all of the temperatures of all of the thermometers went down. And that water was at room temperature. It sat here at room temperature. So the reason it went down is because of the evaporation process. Okay? So you would have something like that.
The cotton ball feels cold.
That's because evaporation is occurring off the cotton ball. If you would, now you can leave it on there if you want to till the end of class, or you can put your cotton ball back in the little glass. But just don't knock the glass of water over onto your books or anything, because your moms will be very excited with me. Does everybody have that now? Did you guys all get that? Yeah, excited is a good word. Do you like that? Okay. All right. So that's your observation part. Oh, let's see. We're on page 31. So we saw that oxygen does affect fire. We saw that it burns more quickly. We saw that it burns brighter if you have more oxygen, and if you have less oxygen, it eventually goes out if you don't have any oxygen, doesn't it? And so the oxygen in the atmosphere has to be diluted for living purposes. And what did God dilute it with? No, oops, gone. Nitrogen. Right, nitrogen, thank you. Okay, and so I think it's Johnny's turn. On page 32, Johnny, would you read 2.3 for us, please?
The scientists want to measure the percentages of nitrogen and oxygen in a sample of air that was not dry. They get greater, less than, or essentially the same percentages shown in figure 2.1.
Okay, did you happen to answer that?
It would be less.
Less, very good. Okay, and just for those people that maybe don't think in these terms, I want to show you. Let's say that this is our 21% oxygen of the dry air, 78% nitrogen, and 1% other. In this question, he actually said, we're going to have a sample that's not dry. So what other piece of the pie do we have to add in here? Water. We have to add water vapor in here. So when we do this, all of these percentages are going to adjust down, aren't they? Just because we cut another piece out of the pie, everything else, these other pieces are a little bit smaller, aren't they? Does everybody see how to think through that one? Okay. That's how we want you to think through that one. Thank you, Johnny. Pierce, would you read 2.4 for us, please?
At high altitudes, there is less air around you as compared to lower altitudes. But a candle at high altitudes burns dimmer, brighter, or essentially the same as the same candle at low altitudes.
Okay, so we have a candle, and we're going to take it to high altitude. Would it burn as bright or dimmer than a... It would be dimmer because there's less oxygen. The closer you are to the to the Earth, the atmosphere is thicker, therefore there's more oxygen. The higher you get, the less atmosphere there is. It's because of the gravitational pull on it. And so there's less oxygen. That means when the Miami Dolphins go to play the Denver Broncos, are they still the Denver Broncos or have they changed that? They are still. Okay, good. They keep changing things. They go to play the Denver Broncos and it's an outside stadium. The Dolphins are at a definite disadvantage because the Dolphins are used to more oxygen at sea level than those guys that play at a mile high all the time. And those guys at a mile high, when they come down here, it's the heat that causes them the disadvantage. But if they come on a cool day, they actually have an advantage because their body's used to living on less oxygen, and therefore it's acclimated to grabbing the oxygen out of the air better. There have been marathon runners that actually trained in the mountains, and then when they came down and ran at sea level, they did much better because their body was already acclimated to the less oxygen that it was at the higher altitudes. I don't know about you, but I get altitude sickness. You get me up in the mountains and I start feeling pukey, because my body goes, you're a sea dweller. You need oxygen. So, yes, Cole.
I know we have a friend who carried around an oxygen mask, didn't need it, but it's not needed for his health or anything, but he had it on for some time. He was going to go deep sea diving or something, and he had it so that it would lower the pressure so he would get used to it. Is that the same reason as this?
Pressure so that he would get used to it. I have no idea why that person did that.
Remember Spencer, he had the oxygen.
Spencer had the mask. It was the same thing. He's training for swimming, so he put the mask on to get used to less oxygen. That's less oxygen in it.
So his body's acclimating to less oxygen is what you're saying.
On and it stimulates air in the mouth.
So that his body gets to where it's more efficient.
Yeah.
Okay, that makes sense. That's a hard. That's somebody that's serious about swimming. Okay.
No, he likes swimming.
Yeah, that's what I mean. He's serious
and it looks
about.
awesome when you put it on. It looks cool.
Us girls are going, really? I don't think so. And the guys are going, yeah, it looks so cool. It's just that difference between guys and girls. Just let it go. Okay, on page 32, we have carbon dioxide in the Earth's atmosphere. Now, a lot of people would tell you that carbon dioxide is a poison in the Earth's atmosphere, but that's not true. If we have too much carbon dioxide that we breathe, it's not good for us. But carbon dioxide is necessary to life on planet Earth. There are two reasons. Can you tell me one of the reasons that carbon dioxide is important?
The greenhouse effect.
Okay, one is the greenhouse effect. Very good. And we'll go into that in just a minute. What's the other reason? Who breathes it?
Plants need carbon dioxide.
Thank you, plants. Thank you very much, both of you. Plants take in the carbon dioxide to photosynthesize and then exhale oxygen. So carbon dioxide is very important, and that's where we get a lot of our oxygen. I'd say the vast majority of our oxygen is coming from the plants. I know almost over 3/4 of it comes from little tiny water plants called diatoms that are in the ocean, but they're still little tiny plants. They're photosynthesizing. It's not the Amazon rainforest. I just want to give you the heads up. Okay, you mess up the oceans, we all die. That's it. Anyway, so anyway, let's talk about what Cole mentioned first, and that's the greenhouse effect, and it's on page 33. I want to start with this. When I was a kid, we used to, at Christmas time, love to watch Frosty the Snowman. Have you guys seen Frosty the Snowman? Okay. In the movie, that's okay, at least you can have the reference. In the movie Frosty the Snowman, the little girl is taking Frosty back to the North Pole because it's warming up and she doesn't want him to melt. And as they're going up there, the little girl gets very cold. And so Frosty finds a greenhouse, and even though it's cold outside, he takes her in the greenhouse, and it's warm in there, and she can warm up. And then he melts, and that's a bummer, and she opens the door, and he comes back, and it's all good. But the point is that, I want to be true to the story. The point is that even though it's really cold outside, it's nice and toasty warm in the greenhouse. Now, carbon dioxide in the Earth's atmosphere helps with the greenhouse effect. It is one of the main greenhouse gases. Water vapor is also a greenhouse gas in the atmosphere, but carbon dioxide is also. And what that does for us is, here's Earth, and we have an atmosphere, so when the sun's warmth comes in, it can't just escape back into outer space. Some of it bounces back and forth in here, and that's what greenhouse gases do. They kind of make it like a blanket around planet Earth so that our atmosphere actually holds in some of the sun's warmth so that we can have, it's the average temperature on the Earth is 50 degrees Fahrenheit. That includes Antarctica, that includes the equator. That's pretty nice, 50 degrees Fahrenheit, you know, if you consider the Antarctica and the equator. It's pretty nice average, isn't it? That's because of the greenhouse effect. So the greenhouse effect is very important. Now, some people might say, well, we're 93 million miles from the sun, and that's why, you know, a little closer we'd be crispy critters, a little farther away we'd be popsicles. So that's really why we're the right temperature. But I want to challenge that idea with you with the moon. The moon is rocking and rolling around us every 28 days, isn't it? Here, you want to put the man on the moon? Here, we'll put him here. There he is. Okay. And so the moon is going around us every 28 days, isn't it? It spins around us. It is the same distance we are from the sun, basically, 93 million miles, because it's cruising around us, right? So obviously, it's not just the distance from the sun. Yes, it's the right distance from the sun, but if you're standing on the moon, did you know that one side of your body, the side towards the sun, is 200 degrees Fahrenheit hotter than the other side of your body? Yeah. I can't remember which astronaut it was that stood on the moon, and when they asked him if he was excited, he goes, yeah, I want to be in a place where one side of my body is 200 degrees hotter than the other side at the same time. And I'm thinking, oh my goodness, that's just like, you know, crazy. But the point is that there's no atmosphere on the moon to keep the warmth in, so one side is super hot and the other side is super cold. A matter of fact, we're going to study this at the very end of the year, but Venus has an atmosphere that's full of greenhouse gases, and therefore Venus is the hottest planet in the solar system, 858 degrees Fahrenheit on the surface of Venus. Yet Mercury is closer to the sun, but it has no atmosphere, and it's not as hot as Venus is. It's because of the runaway greenhouse effect on Venus. So the greenhouse effect itself is a very good thing, especially in the version God gave us here on planet Earth. Okay? A runaway greenhouse effect, like what Venus has got, now that's not a good thing. That wouldn't be good. You know, they can't even send probes to Venus because the atmosphere is so dense that they don't know if the probe would explode from the pressure or melt first, you know, but it wouldn't reach the surface. Yes, Caleb?
Like, do plants make an have something to do with the atmosphere?
Our atmosphere? Yes, they help us to maintain the atmosphere because we're breathing in oxygen and exhaling carbon dioxide, and they're breathing in carbon dioxide and exhaling oxygen, so we have a recycling system going on.
So if we were to start sending plants to other planets, would it made in the atmosphere?
Oh, that's a very good question. I don't think so, and the reason is because life requires several other parameters other than just oxygen. I didn't show you guys a piece of the privileged planet yet, obviously. I showed that to the middle school class. There's a lot of different parameters that have to be met for there to be life on a planet, and oxygen is just one small one of several, and we'll be talking about a lot of them as we go through. That was a very good question, though. I'll try to make sure I show you guys pieces of that movie because it's really good. Okay? The scientists actually call where we are in proximity to the sun the Goldilocks zone. And this is the scientists that call it that because they say it's not too hot, not too cold, just right, you know, and the magnetic field of the Earth has to be just right because it protects us from the sun's cosmic rays. And if it was a little, the Earth was a little smaller and the cosmic field was a little smaller, we'd all be crispy critters. We'd be burned up no matter what the distance was because of the cosmic radiation. The plates of the Earth actually are recycled. And if the recycling wasn't going on, there wouldn't be enough minerals and stuff for us to live on planet Earth. The nitrogen is just right. So if you had all that oxygen being produced on another planet without the nitrogen to dilute it, then you wouldn't have a breathable atmosphere for any life form that we know of at this point. Does that make sense? So there's like all these different parameters that would have to be met. Okay? It was a very good question. Okay, let's go to page 35, please. So people that are worried about runaway global warming would say, and it's true that everything we burn, every time we take a breath, anytime we flip on a light, every time we turn on the car, we're producing carbon dioxide because anytime you're burning anything, and that's why we exhale carbon dioxide is because we're combusting glucose, okay? So anytime you burn anything, carbon dioxide is formed. And there's more people breathing now. We're burning a lot more than we used to. And so we're producing a lot of carbon dioxide. So some people are very concerned about global warming because they're saying we're making more carbon dioxide. And actually, we're going to deal with the global warming thing next week. But look on the bottom of page 35, please. You guys just had to read to 36, right? For this week. Okay, good. I'm just making sure. Now, there's a question that this answered for me that used to really bug me. On page 35, figure 2.2, on the left side, you see inhaled air. 78% nitrogen, 21% oxygen, 1% other. Told you got to know that. On the right-hand side, you see exhaled air. Okay, and you see that you exhale carbon dioxide is added to that and water vapor is added to the pie. Everybody sees that. What used to bug me when I was your age, because I didn't know this, I never learned this in school until I started teaching out of this book. I'd never seen this. All the way through college, I never knew this, okay? And it always bugged me, how does CPR work? And the reason that bugged me is because we breathe in oxygen, we breathe out CO2, so how does me blowing into that person help them? Because all I'm doing is blowing CO2 into them, right? Come on, didn't any of you ever think of that? Come on, nobody thought of that?
I did.
Thank you. I mean, that used to really bug me. I'm going, how does that work? What good is it doing? Then I saw this. Look at this. Look how much oxygen you exhale. Look at that. You exhale 16% oxygen. That means if you blow into that person, there's still enough oxygen to keep them alive. Praise the Lord, right? See, that's how it, doesn't that help you? That helped me. I looked at that and I went, oh, that's how it works. It used to always really bug me. Yes?
I was just wondering, it might, does the faster you breathe, the faster you make the circulation of the blood and the oxygen, the faster you breathe, does that make the oxygen percentage in the total mix higher or lower?
Higher. And that's, when you're doing, let's say you're running, so you start breathing hard. You're breathing hard because not only do your cells need to make more little batteries to keep up with the energy expenditure that you're doing, but also in the process of making those little batteries, your body produces acid, and your body needs to deal with all that acid because if your body becomes too acid pH, it can kill you. And so you start breathing harder and breathing harder trying to help all that. Okay? Let's see, and that's why eventually your body goes, okay, stupid, you're not getting it, and you just knock out. So, because your body goes, if you're not going to get it, I'm going to make sure you do.
And what went wrong with the mix when carbon dioxide went with the carbon monoxide?
Okay, carbon dioxide is that molecule. It's a carbon with 2 oxygens attached to it, and each of those lines represent a shared pair of electrons. And so carbon shares 2 pairs of electrons here and 2 pairs of electrons here. That's carbon dioxide. Oxygen looks like this. O2 is what we breathe. And when our red blood cells come into our lungs, they dump the carbon dioxide and they pick up oxygen to carry it to the cells. So far, so good. So you see these molecules are different, and your body sees them as different. So it picks up the oxygen, dumps the oxygen at the cells, picks up the waste products, carbon dioxide and water vapor, takes it back to the lungs, and we exhale water vapor and carbon dioxide. Carbon monoxide looks like this. It looks similar enough to this that our red blood cells will pick it up, but they can't release it. And this is why when they find somebody that's got carbon monoxide poisoning, sometimes they still can't save them, even though they found them still alive. Because they have to have a blood transfusion very quickly, because the red blood cells, once they hook onto this, can't get rid of it. And so if you don't have enough red blood cells that are still available to pick this up and dump this, it'll kill you. Because now your body can't get rid of this, and it can't pick this up. And so it's like asphyxiating even though you're breathing, because your red blood cells can't do the job they're supposed to do. Does everybody understand?
So it's kind of like a roadblock?
Yeah, very much so. It's kind of like taking all your little pickup trucks and making them not functional, because the red blood cells are like little pickup trucks, right? And it makes them not functional so that you die. It's very dangerous. Very dangerous. We don't have fireplaces here, but people that have fireplaces, that's a real issue, because carbon monoxide poisoning can occur from fireplaces or places where it's really cold and they have to start their cars indoors before they go outdoors. Like in Alaska, they actually have carbon monoxide alarms and they have filters in the garages, and then carbon monoxide alarms to tell you so that you don't have that problem, because you can't smell it. It's a colorless, odorless gas. So it can be very dangerous.
It's not a couch potato.
It's definitely not a couch potato. Not inert. Yes, Brittany?
Also, what happens when you have a fireplace is combustion.
Right, you have combustion occurring, but if you have incomplete combustion, it can cause that black soot. That's showing you have incomplete combustion, which means there's carbon monoxide being produced. So then the idea is to blow air into the fireplace, and I've always looked at that and gone, but that's kind of counterproductive, because the whole idea was to get the heat from the fire. So anyway, I'm not exactly sure how to work the fireplace thing, because I'm a South Floridian, and I'm sorry. Anyway.
The fire gets hotter.
Yes, it does get hotter because you're feeding it oxygen, but then you're kind of losing the heat too. But I guess you could still aerate the area. So anyway, let's finish this up on page 36. The 2 ways of producing carbon dioxide are to have fires and living things burning things, and that also provides more carbon dioxide being added to the Earth's atmosphere. We need to do 2.5 and 2.6. Who read last? Did Caleb? Did you read yet? David, did you read? Pierce read last. Okay, so David, would you read 2.5 for me, please?
Yeah. We know that if carbon dioxide contains
Concentrations
we're too low. Plants who starve couldn't.
It's a long one. You want me to do this one?
Sure.
You can answer it for me. How's that?
Yeah.
All right, deal. We know that if the carbon dioxide concentrations were too low, plants would starve. Conversely, experiments indicate that many plants actually flourish. That means they're real happy when the concentration of the carbon dioxide in their vicinity increases. How can this fact help explain why some experiments indicate that household plants tend to grow better when their caretakers talk to them? So why would plants do better when their people talk to them? What are we breathing on the plant when we talk to them, David?
Carbon dioxide.
That's right, and that's what they like, right? Good. Plants do, though, grow towards soft music and grow away from rock and roll music. Plants can apparently sense more things than what some of us realize. So, but there you go. It's because we're breathing the carbon dioxide on them.
They'll grow.
Oh, yeah. People have done those experiments for years for science projects. Caleb, would you, do you want to read that, or you want me to read it and you answer it? Okay, 2.6, please.
know that our bodies do not use nitrogen we inhale. Nevertheless, in figure 2.5, notice that the percent of nitrogen in exhaled air is lower than the percent of nitrogen in inhaled air. If our bodies do not use nitrogen in any way, why does the percentage decrease? The mixture becomes more polluted and decreases the percentage of nitrogen.
Good. You have more pieces of the pie, don't you? Very good. And therefore, everything becomes less. Are we okay on that? All right. Watch your syllabus because, yeah, here, you're supposed to do the global warming reading next week. It's a separate article, okay? So make sure you do that. And we have to clean up the lab, so don't leave. We've got to clean up the lab. Have a Jesus-filled week.